Today we'll write the Clipper contract. The Clipper contract is a contract that sells users collateral. The collateral is sold by a Dutch auction, and the auction is started by the dog contract by calling the function called kick. So a user will call the function bark on the dog contract. The dog contract will call the function kick on the Clipper contract, which will start the collateral auction. The collateral auction contract is located under a file called clip.sol. I'll copy this. And then inside our terminal, let's create a new contract called collateral auction.sol, and then paste the code. Okay, next I'm going to first import some contracts that we're going to need. These contracts are the math library, the auth contract, and the guard contract that handles reentrancy lock. Next, let's rename the interfaces. The bat-like will be our ICDP engine interface, which we can import, so I'll remove this, and then import ICDP engine from interfaces ICDP engine.sol. The pip-like interface will be the price feed, so let's rename this as iPriceFeed. It has a single function called peak, and it will return bytes32 and boolean. Bytes32 will represent the value that this price oracle returned, and boolean will represent whether the call was successful or not. Inside our contract, we change the type of bytes32 to uint256. The unit for this uint256 that will be returned will be wed. Okay, moving on, we have the spotter-like interface. Let's rename this as iSpotter. The function par will represent the value of the stablecoin, and the unit will be in rate. The stablecoin targets one stablecoin equal to $1, so par will return one rate. And then next we have the function called IOKS, which will take in bytes32 that represents the IOK, and then it will return two things: the interface for the pip-like, so this will be the interface to the iPrice feed, and a uint256. Let's go back to the spotter contract that we wrote in one of the previous videos, and inside here we rename the struct IOK to collateral. So let's copy this, and then going back, I'll paste it here. And then for IOKS, we'll say collaterals. For the input, it's going to take in bytes32 col type, and it's going to return, let's say, the collateral struct, collateral memory. The dog-like interface, let's rename this as the iLiquidation engine. The function chop will return the penalty given the collateral type. So let's call this penalty. The function digs will rename it as remove coin from auction. The first input will be col type, and the second input will be the amount of coin to remove from the auction. The unit will be in red. The Clipper quality interface is a contract that is called when an auction is successful. Let's call this as iCollateral auction quality. And this is the function that will be called. Let's call this callback. And the inputs will be the caller, the amount of DAI that is owed, O, the amount of collateral to claim, slice, we'll call this, and some arbitrary data. This is a contract that handles the calculation of the price of the collateral. Let's call this iAuction price calculator. The inputs will be the starting price and the time elapsed. Let's call this DT. And it will return the price of a collateral. Okay, and then we have the contract Clipper. Let's rename this as collateral auction. And you see some logic for the authorization. I'll remove all of this. And this collateral auction will be auth. And we're also going to need the guard contract to guard against reentrancy, guard. Okay, next let's move on to renaming the state variables. Bytes32 public immutable IOK. This will be the collateral type. So I'll rename this as collateral type. The bat-like, we rename this as ICDP engine, CDP engine. Dog-like will be the interface for the liquidation engine, iLiquidation engine. And then the address of the val contract, we rename this as DS engine. Spotter will be iSpotter. Calc will be the iAuction price calculator. Okay, and then next we have some state variables. Buff will be a number that is multiplied to the starting price of the collateral. Let's call this boost. Tail will be the maximum duration for an auction. Let's call this max duration. Cusp will be the percentage drop before auction can be reset. Let's rename this as min delta price ratio. Once the price has decreased from the starting price to some price, and when the ratio is less than this, then the auction can be reset. Chip will be the percentage of DAI that is given to the caller that started the liquidation. And tip will be a flat fee also given to the caller that started the liquidation. Let's call this flat fee. And then we have a state variable called chost. This will represent the minimum that each collateral must have. This is called IOK dust, multiplied by the penalty of that IOK when it is liquidated. Let's rename this as min coin. Kicks will represent the total auction that has been initialized so far. And it will also represent the last auction ID. So let's call this last auction ID. And the array active will represent the currently active auction IDs. We'll keep it the same. Okay, moving on, let's rename some of the fields inside the struct. Position will represent the index and the active array. Next, we have a field called tab. This will be the amount of DAI to raise. Let's rename this as coin amount. That will be the amount of collateral to sell. Let's call this collateral amount. And USR, user, will be the liquidated CDP. Let's call this user. Tick will be the time that the auction started. Let's call this start time. And the starting price, let's rename this as starting price. And then we have a mapping from UN256 to sales. UN256 will be the auction ID. And then we have a variable called locked, which is used for the reentrancy lock. This is handled by our contract called guard, so we can remove this. Okay, next we have a state variable called stopped, which will stop the functions at different levels. And the levels to be stopped are explained over here, so I'll just move on. Next we have events. To keep this video short, I'm going to remove all of this. And we move on to the constructor. Bat, I'll rename this as underscore CDP engine. And spotter, I'll rename this as underscore spotter. Dog, I'll rename this as underscore liquidation engine. And IOK, I'll rename this as underscore collateral type. Okay, next I'm gonna rename these state variables. Bat will be CDP engine. Interface will be iCDP engine. Spotter will be iSpotter. Dog will be liquidation engine. IOK will be collateral type. Buff will be boost, and it's initialized as rate. And then we have some logic for authorization, which we do not need. Okay, next we have a modifier called lock. This is handled by the guard contract, so we don't need this. And then we have a modifier called is stopped. Requires that the current state variable stopped is less than level. Okay, moving on, we have some functions. File. These are all simple functions. So to keep the video short again, I'm going to remove all this function. And then the same for the math. This is all inside our math library. I'm going to keep removing all of the functions that we're not going to need in this video. So scroll down, and then we'll remove these two functions, count and list. Count the number of active auctions and list the active auctions. Get status, we're going to need this, so we'll keep it. Status, we're also going to need this. And then upchost, we're also going to need this. And yank. Yank is a function that is called during emergency shutdowns. The code is simple, so I will not explain here. And also remove this. Okay, so let's start with some of the functions that we're going to need for the auction. There are 3 functions for the auction. The first one is called kick to start the auction. And the next one is called redo to restart the auction if nothing was sold. And then to close the auction, a buyer will call take. If all of the collateral is sold or all of the debt is repaid, then the auction ends. We'll come back to this later. Let's scroll all the way down and start by reworking some of the internal functions. Actually, let's start by upchost. This function is going to get the minimum debt configured for a collateral type. This is stored in dust, and then it multiplies by the penalty of the collateral if it was to liquidate it. Multiply these two and store it in a state variable called chost. Chost, we renamed it as min coin. So let's rename this function as update min coin. The first thing that we need to do is get the collateral. iCDP engine dot collateral memory call is equal to iCDP engine, CDP engine from the state variable dot collaterals, and then pass in the collateral type. And then we can remove this code. And this dust will be call.min debt. Next, it calls the liquidation engine dot penalty for the collateral type. Then to multiply, we'll do math.wmul. Okay, that completes the function upchost. Let's move on. Let's rework the function status. This is an internal function. For the input, it's going to take in the starting time and the starting price. Let's rename tick as starting time, and then top, we'll rename it as starting price. And this function will return 2 outputs. Done, whether this auction is done or not, and also the price, the current price. The current price is calculated by calling the calc contract, passing in the starting price and the time elapsed. So this will be block.timestamp minus starting time. And then done is calculated by checking if block.timestamp minus the starting time is greater than tail. Tail, we renamed it as max duration. And the other condition is if we divide the current price by the starting price, then the ratio should be greater than min delta price ratio. If the ratio of price divided by starting price is less than the minimum, then the auction is finished. Okay, that's the function status. Let's move on. Get status. This is an external function, so we're not going to need for this video. I'll just simply remove this. And then we have an internal function called remove, which I will come back to later. The next function that I want to work on is called getFeedPrice. What this function will do is get the price of the collateral directly from the price feed. So let's rename this as getPrice. And it's going to return the price. The first thing it does is get the contract for the price oracle from the spotter contract. Spotter.collateral memory col is equal to spotter.collaterals, passing in the collateral type. Then we can remove this. Once you have this struct collateral, it will store the address of the price oracle. So here, let's say I price feed call.price feed, and then call the function peak. The outputs that will be returned is a UN256, value of the price of the collateral, and Boolean. We'll require that the Boolean that was returned is true. And the price is calculated by multiplying this value by BLN. BLN is 10 to the 9, 1E9. And then it does a rdiv with the par fetched from the spotter contract. Okay, so that completes the function getPrice. Let's move on. And let's rewrite the function kick. This is a function that is called to start the collateral auction. Tab will be the coin amount to be raised. Let's call this coin amount. Lot will be the collateral amount that is sold. Let's name this collateral amount. USR will be the address of the CDP. This will be the address that will receive any leftover collaterals. And then KPR will be the keeper, which will receive the incentive for starting the function kick. Next, it does some checks that coin amount is greater than 0. Lot will be collateral amount is greater than 0. The CDP address of the CDP is not equal to the 0 address. And then creates a variable called ID. This will be last auction ID. And then checks that ID is greater than 0. Since overflows will result in an error in solidity 0.8, we can remove this. It first pushes this new auction into the array active. And then it stores this information into the sales struct for the ID, sales of ID. Position will be active.length -1. Coin amount will be coin amount. Lot will be collateral amount. USR will be user. So this will be user. So let's rename this as user as well. And then tick will be the starting time. Start time. It first calculates the price to start the Dutch auction. This state variable is called top. This is done by calling math.rmul and then calling the function getPrice multiplied by the boost. This price that's been increased will be the starting price of the Dutch auction to sell the collateral. So let's rename top as starting price. Checks that starting price is greater than 0 and then sets the starting price for the struct sales store that ID. Okay, the next part is calculation of the fee to be given to the caller that started this liquidation. Here it's caching the state variables into a local variable. To keep this code simple, I'll simply remove this. Tip will be the flat fee if flat fee is greater than 0, or if chip is fee rate is greater than 0, then we need to calculate the amount of coin to mint to this keeper address. Let's rename this coin as fee. So this is add to the flat fee, multiply coin amount by chip, which is the fee rate, and then call CDP engine dot mint to the keeper. The det will go to the val contract, and the amount to mint is fee. So that completes the function that will start the liquidation. Actually, let's rename this as start. Moving on, let's rewrite the function for redo. This will restart the auction. The inputs will be the ID of the auction to restart and the keeper address. First, it's going to assign some state variables to a local variable, user. Tick will be the starting time. and top will be the starting price. It checks that user is not equal to the 0 address. Next, it checks the status and makes sure that the previous auction is finished. Here again, tick will be the starting price, top will be the starting price, and tick will be the starting time. Next, it assigns some state variables to a local variable. Tab will be coin amount, and mount will be collateral amount. And then it resets the starting time to the current timestamp, block.timestamp, starting time, and then recalculates the price by calling the function getPrice. Top will be the starting price again. And again, we'll need to do a multiply, math.rmul, the current price of the collateral boosted by the boost. Check that starting price is greater than 0 and then set the starting price. Again, the next part is calculation of the fee that is to be minted to the caller of the function redo. So when someone restarts an auction, they'll earn some stablecoin. Again, let's rename coin as fee. And if the flat fee or the fee rate is greater than 0, then we rename chost as min coin. If the coin amount is greater than min coin and the collateral amount multiplied by the price is greater than min coin, then fee is equal to the flat fee plus multiply the coin amount by the fee rate. And this amount will be minted to cdp engine.mint. The debt will go to the BAO contract, the DES engine contract, minted to the keeper for the amount fee. And then we'll remove this event. Okay, so that completes the function redo. Okay, moving on, the last function that we'll rewrite is the function take. Once the auction has started, the price of the collateral will start decreasing. When the price is right, a user will call the function take to buy the collateral and then pay the coin amount. The inputs will be the ID of the auction. Next is amount. This will be the maximum amount of collateral to buy. Let's rename this as max collateral. And then next, the input max will be the max price. Max price. Next will be the receiver of the collateral and the data to send to the receiver. First, it stores some state variables into a local variable again. USR will be user and tick will be starting time. Actually, this should be start time. Okay, and then moving on, it checks that this user address is not equal to the 0 address. And then it calculates the current price. Get the current price in the status, start time, and then pass in starting price. Check that this auction is not done yet, and then get the price. Okay, and then moving on, it makes sure that this price, the current price, is less than or equal to the max price, and then caches the collateral amount to a local variable, collateral amount. Tab will be coin amount. And then it initializes a variable called O. O will be the amount of coins that is owed to this auction. And this amount will depend on the amount of collateral that the user requested to take. It calculates this by taking the minimum of the collateral amount that is sold with the max amount that the user specified. And then the amount of coin that is owed is calculated by multiplying this amount of collateral multiplied by the price. Moving on, next checks that this amount of coin that is owed is less than or equal to the amount of coin that the auction needs to collect. If the amount that is owed, calculated here, is greater than the coin amount to be raised, then set O to the coin amount, and then we'll need to recalculate the amount of collateral to give to the user. This is done by taking this O and then dividing by the price. And the way to think about this is if you multiply this number slice by the current price, you'll get the amount of coin that is owned. And this is equivalent to this part of the code. Okay, and then moving on. Else, if the amount of coin to owe is less than the coin amount, and the amount of collateral slice to take is less than the collateral amount, then we need to make sure that there is no small amount of collateral left or amount of coin left after someone takes out some of the collateral from this auction. So if coin amount, the amount to raise, minus the amount to be repaid, O, is less than min coin, then we require that coin amount is greater than this min coin, and then we'll recalculate the amount of coin that is owed and the amount of collateral to give to the user. O will be coin amount minus min coin. And slice again will be calculated by dividing O by the current price. Okay, and then moving on. Next, it updates the local variable for coin amount and collateral amount. Coin amount is minus equals O, and collateral amount is minus equals slice. Next, it calls the CDP engine to transfer the collateral. CDP engine dot transfer collateral for collateral type from address this to the receiver specified by the input for the amount slice. Okay, and then next, if data is greater than 0, and if the receiver is not equal to the address of the CDP engine, and receiver is not equal to the address of the liquidation engine, then call I collateral auction callee at receiver, call the function callback with the inputs, message sender O, slice, and data. Okay, and then next it gets the DAI from the caller. So this will be CDP engine, transfer coin from message sender to the DS engine for the amount owed. Next it calls the liquidation engine dot remove coin from auction for the collateral type, and the amount is calculated by saying if the collateral amount, the remaining collateral amount, is equal to 0, then remove all of the coin amount plus the amount that is owed. Otherwise, just remove the amount that was owed. Okay, and then moving on, if the collateral amount is equal to 0, then remove this auction. The auction is finished. Otherwise, if the coin amount is equal to 0, coin amount, then call the function CDP engine dot transfer collateral for the collateral type from this contract to the user. This will be the CDP for the amount, collateral amount, whatever collateral amount that is remaining. And since all of the coin has been repaid, remove this auction. Otherwise, we update the coin amount and the collateral amount. And that completes the function. Now the last function that we'll work on is remove. What it basically does is copy the last element into the index that is to be removed and then remove the last element. So we don't have to rewrite any logic here. Let's try compiling the contract. Inside my terminal, I'll type forge build. Okay, so I don't have a contract called guard. So inside the lib, I'll create one. And here it is. It's just a contract with a reentrance lock. Okay, let's try compiling again. Okay, and our contract compiled successfully.